Good morning to all. Welcome to the session on vibration measurement. As per our syllabus, we have to study the basic principles and operation of vibrometers and accelerometers. Reasons for measurement of vibrations. That is, the first reason is to check the health of machines. Next is to understand the dynamic behavior of the machine components, and it helps to identify important parameters such as mass, stiffness, and damping. And in some cases, the machines are running at very high speeds, which may cause its resonant conditions and they may get fail. So we need to know what is the resonant condition for a part and what is the chance of failure. And in some situations, excessive vibrations may transfer to the nearby machines or structure. Now, the vibration analysis of a mechanical system. So in vibration analysis of a mechanical system, it required to measure the displacement, velocity, and acceleration components of a system. So measuring displacement, velocity, and acceleration components are known as vibration analysis of a mechanical system. So the instrument which is used for this vibration analysis is known as vibration measuring instrument or seismic instrument. The picture of a seismic instrument is shown here. In this picture, we can see that there is a suspended mass M, which is suspended on a spring of spring constant K and a damping port having a damping coefficient of C. And this entire arrangement is housed inside a frame, and this frame is fixed over the machine part whose vibration has to be measured. Let Y be the base excitation of the machine component or the vibration of the machine component to be measured. That is, it is in SHM, assuming S in simple harmonic motion, and let X be the absolute displacement of the seismic mass, that is the displacement of the entire structure. Then Z is recorded on this scale, and this Z is the displacement of seismic mass relative to the frame, because M is the seismic mass, so it will have a movement, up and down movement, relative to the frame movement. So that relative motion is measured as Z. The displacement Z is recorded by the instrument, and with the proper suitable calibration, we can convert this seismic instrument as a vibrometer or a velometer or accelerometer. The two types of widely used seismic transducers are vibrometer and accelerometer. So vibrometer is a device to measure the displacement of vibrating body. On the other hand, the accelerometer is an instrument to measure the acceleration of a vibrating body. So the same seismic instrument can be used for measuring the displacement or the acceleration. So the condition is such that if we use low natural frequency, that is omega n, then it is vibrometer. If we are using high natural frequency, then it is accelerometer. So vibrometer is known as low frequency transducer and accelerometers are known as high frequency transducers. Let's consider the equation for forced damped vibration, where Z by Y is given as R square divided by root of 1 minus R square the whole square plus 2 zeta R the whole square, where R is the ratio between frequency to be measured divided by natural frequency, and zeta is the damping ratio, which is given by C by Cc. C is the damping coefficient and Cc is the critical damping coefficient. Now let's see this figure. In this, the Z by Y values are plotted against the R values. So in this figure, it can be seen that for large values of omega by omega n, that is the R, the ratio of Z by Y approaches unity. That is, in this region it approaches unity for every value of damping. So whatever may be the value of zeta, it approaches to unity. So this feature is used for constructing the vibrometers. So in this equation, for larger values of R, that is R is greater than 3, then we are neglecting this portion because this one is negligibly small. So this equation becomes Z by Y is equal to R square divided by root of 1 minus R square the whole square. So this is approximately equal to 1, that is approaching to 1. Otherwise we can tell that this Z is approximately equal to Y. So the Z is equal to Y means Z is the indication of the instrument and Y is the feature to be measured. So Z is the output signal and it's a true reproduction of input quantity Y. We already discussed that vibrometers use low natural frequencies and the natural frequency omega n for vibrometers are ranging between 1 Hz to 5 Hz. Since vibrometers are low frequency instruments, these are used for measuring the vibration of huge structures like buildings and railway bridge, etc. And the disadvantage part, this one is actually used for vibrations of huge constructions or huge components. The size of seismic mass should also be higher. So the instrument itself is heavier in construction, so this application is limited. In the next session of this topic, we will continue with the accelerometers. So thank you for watching and stay safe.